Okay, so far we've talked about frequency distributions and histograms. And in this lesson, we are going to touch on tons of other types of graphs. And so the title of the section is Graphs That Enlighten and Graphs That Deceive. So we're going to go through the enlightening graphs first. Obviously, deceive is typically having a negative connotation. Deceiving graphs are not graphs that we want to use. Since statistics is a science, we want things to be accurate, and those that deceive are not. So if you are, trying to create graphs, to back up research, things like that, you would want to use enlightening types of graphs. So most of these types of graphs you're going to be very familiar with, some since probably elementary school, others of them will be new. So first one is a dot plot where each data value is plotted above a number line and the repeats are stacked on top of each other. So if you have two data points at, 5, you would have a 2 dot height there. Features of a dot plot that are helpful is it shows the shape of the distribution, because obviously with the stacking, it's kind of like having bars, you can see which ones have the most. The other thing that's nice about a dot plot is that we can work backward and approximate the original data. That's something that we can't do in a frequency distribution or a histogram because we have classes, it's a range. We can tell how many data points fall in that particular range or in that particular bar, but we have no way of knowing what the actual individual data pieces were from those two. From a dot plot, we can. So that's kind of a nice feature, is that we could work backward to see the original data if we wanted to. Then we have a stem plot. This is also sometimes called a stem and leaf plot. And this is where we have data values separated into two parts. The stem, which is the left digit, usually the tens place. If you would have something that had 3 digits, then you would take the first 2 digits. And then the leaf is the right digit, always just 1. So typically the stems are the tens places, the leaves are the ones places. Things we like about a stem plot, similarly to a dot plot, you can also kind of see the shape of the data. And here we can get exact original data. We can see what the actual numbers are. Not just an approximation, like on a dot plot, but exactly. Bar graphs, you've talked about for forever, done these since elementary school. You have bars of equal width, but usually on a bar graph you have spaces or gaps between. You don't have to have gaps between, but typically bar graphs do. That show the frequency of qualitative or categorical data. So a histogram, we have numerical data. A bar graph, we do not. So typically we do bar graphs, like in kindergarten where you made a class graph of what your favorite ice cream flavor was, that type of thing. So we've got qualitative data for a bar graph. Usually there are spaces between the bars, unlike with a histogram. The features of a bar graph is it shows the relative distribution and as a opposed to just looking at the original data itself, it makes it easy to compare the categories. So you can very quickly see, how many more kids liked chocolate ice cream than vanilla ice cream, for instance. Time series graph, I'm sure you've used in science class. These have time as your horizontal axis. And your points are connected. Now, when you connect the dots in a time series graph, it is actually connecting one dot to the next dot. It is not, a time series graph does not have a line of best fit. It's actual connect the dots. So the feature of a time series graph, the only reason we would use this type of graph is to show trends over time. So you can see, whether sales have been increasing, decreasing, staying the same, those types of things. Pareto chart is definitely a new one. Most students have not heard of a Pareto chart before. A Pareto chart is a bar graph where the categories are arranged in descending order. So meaning that the category that has the highest frequency is on the left, the category with the lowest frequency is on the right. So a Pareto chart, because it's a type of bar graph, it has all of the same features as a bar graph. However, the main thing that sets a Pareto chart apart differently is that it draws attention to the most important categories. So sometimes the most important are the highest, sometimes it's the lowest, but those become very obvious when we're dealing with a Pareto chart. Pie chart, this one you all know, you've seen a million times, uses slices of a circle where the size of the slice represents the relative frequency, so the percentage. Feature of this is that makes it easy to compare the percents or relative frequencies. So when you look at the size of the slice, it becomes very obvious the highest percentages and how much bigger it is in comparison to some of the other categories. A frequency polygon is created by connecting the points that are above the class midpoint values of a histogram. So again, all those definitions that we talked about in section 2.1, where we defined class width, class midpoint, class boundaries, I think and I hope that you can see how important it is to know those definitions because they get used for other things. A relative frequency polygon, same thing as a frequency polygon, except that we're working with a relative frequency histogram instead of a regular histogram. You have to make sure when you do either of these, either the frequency or relative frequency polygons, that you put start and end points. Because if you only do the midpoints themselves, you actually haven't created a polygon because you haven't closed it off. So I'm going to do an example here of a relative frequency polygon, and I'm just going to pull up our notes from 2.2 where we had the histogram because it's going to be a lot quicker to just show you based on the histogram. So here's the histogram that we did, And again, what we do is we take the class midpoints, which are halfway between the upper and the lower class limits. So in this case, they'd be right at the middle of each of the bars. And it says connecting the points above the class midpoint values. So if you just make a dot for each class midpoint, and then, like I put with the asterisk here, we have to make sure to put start and end points on there as well. So it goes right here is the start, here is the end, and then all we do is connect the dots. So connect the first point to the second point. Connect the second point to the third point. Again, we're not doing a line of best fit here, we're just playing connect the dots. Now, the final connection is along that horizontal axis. So what we've created here is a polygon. It's closed. It has all segments for its sides. It's got vertices. So this would be a frequency polygon for the pulse rates of Math 150 students. So if you're creating this in your homework, you actually have to create the histogram first so that you can get all the midpoints. If you already have the histogram, like I have here, then that makes it super easy. Just make the dots and connect them. So relative frequency polygon, you would do the same thing. So we would just make the dots here, connect them, and we'd be done with that. So this one and the Pareto chart are probably the two newest ones. So those are the ones you probably want to focus on the most, making sure you know how to create them since they're new. All right. So that's how we create a frequency polygon. I wanted to make sure to illustrate that. Now we're going to talk about the graphs that are deceiving as opposed to enlightening. So we've only got two here, and really one isn't a type of graph specifically, it's just something that sometimes happens in graphs. So the one main type of graph that is pretty much always a bad idea if you're actually wanting your data to be represented accurately is a pictograph. Pictograph is where we have drawings of objects where the size of the picture is based upon the data value. So I'm going to give an example here from your book. Let me just pull it up here and adjust my size. So this is an example of a pictograph. So we've got some information, some stats down here, some data, and then we've got a picture that goes with it. So you may not realize right away what's wrong with these, because if you look, okay, well 37% is obviously much bigger than 18%, and when we look at the picture, the size, we can definitely see that it's a lot bigger. And notice we've got copyright giving credit here to our source. This is their picture, not mine. The problem is that when you are using a picture, statistics are a one-dimensional data point. And when we are using a picture, it is either going to be two-dimensional or three-dimensional. So here's what we're going to write down. It uses a 2D or 3D picture to represent one-dimensional data. What this does is it exaggerates the differences. So if you think about it, what we had in this picture is, 37% is not much more than double the size of 18%, because if we do 18 times 2, we'd get 36. So it's about twice as much for the 1970 data. However, because this picture has a length that's twice as much and a width that is also twice as much, that means that the actual area is going to be more than 2 times as big. Because if we do the math there, let's say that my original was, I don't know, 2 by 2, just for ease of numbers. If I double each of those, now I have 4 by 4. The area here is 4, the area here is 16. I have now made a picture that is actually 16 times as big when the actual data piece shows that it's only about twice as big. So it really exaggerates the differences. If you have a 3D picture, it's even more so, because if I went, from 2 by 2 by 2, and then now suddenly I'm doubling them all, 4 by 4 by 4, now I'm going from a total of 8 to a total of 64. So huge, huge, huge differences. So very important that you know that we really should not trust pictographs, because it's relying on our eye, and our eye is going to take in the area, going to take in the volume. So pictographs are deceiving. We never want to use those. The other thing that isn't a specific type of graph, but it's something that is done in a lot of graphs that makes them deceiving, and that is using a non-zero vertical axis. So you can look in your text in the reading, they definitely give you some examples of this, but when you start your vertical axis at something other than 0, it can make the differences a lot more exaggerated, just like a pictograph does. Now, this isn't always the case. Sometimes, in science, they'll have you do a break in the graph. So it's not always creating deception, but if you're talking about any type of histogram or bar graph, it will create deception. Time series graph, probably okay, because you're not going to have values, below the break and values above the break. So make sure you take a look in the text in your reading for examples of that non-zero vertical axis, which in most cases we want to avoid. All right, I think that should set you up pretty good for the homework. Make sure that you ask if you have questions.